In this video, we are going to be seeing about the 22nd module of the ISS, the Columbus Laboratory Module. Let's start the video. The Columbus Module is a European research facility that is part of the International Space Station ISS. Launched in 2008, it is Europe's primary contribution to the ISS and is used for scientific experiments in microgravity across various fields including biology, physics, material science, and much more. The module attached to the ISS provides state-of-the-art laboratories for researchers from the European Space Agency and other international partners, enabling cutting-edge research that benefits life on Earth and space exploration advancements. The Columbus module houses an externally attached payload or experiment hosting facility known as the Bartholomew. Installed in 2020, Bartholomew is managed by Airbus and provides additional space for scientific experiments outside the ISS, allowing direct exposure to the space environment. It supports a range of payloads including Earth observation, material testing, and space technology demonstrations. With its commercial approach, Bartholomew offers simplified access for researchers and companies to conduct experiments in low Earth orbit, further enhancing the research capabilities of the Columbus module. The Columbus module supports a wide range of scientific research in microgravity, enabling experiments that are impossible to conduct on Earth. Research in life sciences including studying the effects of long-term space travel on the human body, such as muscle atrophy, bone loss, and immune system changes. This research helps improve astronauts' health for future missions and has medical applications on Earth, like treating osteoporosis and muscle degeneration. Physical sciences research in Columbus module includes fluid dynamics, combustion, and material science experiments. In the weightlessness of space, researchers can study the behavior of fluids and gases more precisely, aiding in the development of more efficient combustion engines and advanced materials. Experiments in material sciences often focus on creating stronger alloys and understanding the formation of crystals in space, leading to innovation in industrial manufacturing and pharmaceuticals. Technology demonstrations and Earth observations are also key activities in the Columbus module. New space technologies such as advanced sensors and robotics are tested in the space conditions before wider deployment. Earth observation experiments help monitor climate change, natural disasters, and environmental changes, contributing valuable data for understanding our planet's ecosystem and improving resource management. The Columbus module is located on the starboard side common berthing mechanism of the Harmony module of the International Space Station ISS. Harmony serves as the connecting node for various ISS modules, and Columbus is attached to its starboard side, providing access to the station's laboratory facilities. This position allows Columbus to be integrated into the station's power and data systems while facilitating easy crew access for experiments and maintenance activities. ESA contracted EADS Astrium Space Transportation as a prime contractor for the overall design, verification, and integration of the Columbus module. Alcatel Alenia Space, based in Turin, Italy, was responsible for designing and qualifying key components, including the Columbus module structure, micrometeor protection system, and active and passive thermal control systems. These components, along with ground support equipment, were pre-integrated into what was known as the Pre-Integrated Columbus Assembly (PICA). In September 2001, the Columbus module was shipped to Bremen, Germany, where the final system-level assembly and qualification took place at the EADS Astrium Space Transportation facilities. The completed Columbus module was then transported to NASA's Kennedy Space Center aboard an oversized Airbus Beluga aircraft. In November 2007, after undergoing final preparations at KSC Space Station Processing Facility, Columbus was carefully installed onto the payload bay of the Space Shuttle Atlantis for launch. The Columbus module was constructed using a variety of advanced materials designed to withstand the harsh conditions of space. The primary structural components were made from aluminum alloys known for their lightweight yet strong properties, which are essential for reducing launch weight while maintaining durability. For additional protection, the model features a micrometeorite protection system made of materials such as Kevlar and Nextel, which shields the structure from space debris and micrometeorite impacts. The thermal control system uses insulation materials to maintain internal temperature stability. The Columbus module was launched as part of the ISS Assembly Mission 1E on STS-122, marking the first prominent European assembly mission to the International Space Station ISS. This mission was crucial for the European Space Agency ESA as it delivered the Columbus Science Laboratory to the ISS, representing Europe's first prominent research facility in space. The mission was flown by Space Shuttle Atlantis on the 121st overall flight of the Space Shuttle program.
2, 1, 0 and liftoff of Space Shuttle Atlantis as Columbus sets sail on a voyage of science to the space station.
STS-122's primary objectives was to deliver and install the Columbus Laboratory, along with several scientific payloads. Columbus was packed with various experiments such as the Biolab, Fluid Science Laboratory FSL, European Drawer Rack EDR, and European Physiology Modules EPM to enable wide range of research in space. The mission also carried additional equipment, including the Solar Monitoring Observatory and the European Technology Exposure Facility EUTEF, among others. The crew of STS-122 was composed of 7 astronauts: Commander Stephen Frick, pilot Alan G. Poindexter, and mission specialists Leland D. Melvin, Rex J. Wilhelm, Hans Klegel, Stanley G. Love, and Leopold A. Hartz. French astronaut Leopold A. Hartz, representing ESA, was replacing Daniel M. Tani on Expedition 16. Tani, who had been on the ISS for several months, returned to Earth aboard Atlantis. However, the mission faced significant delays prior to launch. The original launch date was set for December 6, 2007, but problems with the engine cutoff, eco sensors, caused multiple scrubs. On the first launch attempt, 2 of the 4 eco sensors failed, forcing a postponement to December 9. During the second attempt, the same sensor issue occurred, resulting in another scrub. The sensors are critical as they prevent the shuttle's engines from running without fuel, which could lead to catastrophic failure. NASA engineers conducted a series of tests and identified the problem in a connector between the external tank and the shuttle. After replacing the connector, the shuttle was successfully launched on third attempt on February 7, 2008. Once in orbit, the crew of Atlantis spent Flight Day 2 engaged in crucial tasks to prepare for the docking with the International Space Station ISS. Their day began with the installation of the central camera, which is essential for guiding the station's approach to the station, followed by the extension of the orbital docking system ring. A significant portion of the day was dedicated to a thorough inspection of the shuttle's thermal protection system using the orbital boom sensor system and the RMS Canada 1. On flight day 3, the shuttle's crew meticulously worked through the rendezvous timeline, executing several engine burns to fine-tune Atlantis' approach to the International Space Station ISS. At 16:24 UTC, Atlantis performed the rendezvous pitch maneuver, allowing the ISS crew to photograph the shuttle's thermal protection system with high-resolution cameras, focusing particularly on the starboard OMS pod, where a raised blanket had been identified as an area of interest. By 1717 UTC, Atlantis successfully docked to the ISS, becoming the first orbiter to dock to the new location of the pressurized mating adapter on the Harmony module. After performing leak checks, the hatches between the shuttle and the station were opened at 1840 UTC. Later, Flight Day 5 was a significant day for the mission, marking the installation of the Columbus Laboratory Module on the International Space Station ISS. After the crew's wake-up call, preparations for the mission's first phase were commenced. Astronauts Stanley Love and Rex Wilhelm suited up, and the EVA started slightly ahead of schedule at 14:13 UTC. They were supported from inside by pilot Alan Pondexter and mission specialist Hans Klegel, who assisted in coordinating the tasks. By 1953 UTC, Stanley and Wilhelm had successfully prepared the Columbus module for unberthing from Atlantis' payload bay, while Leland Melvin operated the station's robotica from inside the ISS. The Columbus Laboratory module was carefully lifted out of the shuttle's payload bay and maneuvered into position. The module made its first contact with the ISS Harmony starboard side at 21:29 UTC. On flight day 6, the crew dedicated their time to activating and outfitting the Columbus module, the newest addition to the ISS. Representing the European Space Agency, Hans Klegel and Leopold A. Hertz became the first crew members to enter the Columbus module during a partial ingress at 28 UTC. A. Hertz acknowledged the movement, expressing gratitude to the European and US teams who made the module a reality, and to other citizens supporting space exploration. On flight day 7, the shuttle and the station crew focused on preparations for the second spacewalk. Station Commander Peggy Whitson and Shuttle Commander Stephen Frigg assisted spacewalkers Rex Wilhelm and Hans Klegel in suiting up and working through the pre-EVA procedures. The spacewalk officially began at 14:27 UTC and concluded at 21:12 UTC, lasting nearly 7 hours. During the EVA, Wilhelm and Schlegel successfully replaced a nearby depleted nitrogen tank assembly on the P-1 truss with the full one that had been delivered by Atlantis. On flight day 10, the crew continued outfitting the Columbus module while Atlantis fired its propulsion system to raise the ISS altitude by 1.4 miles in preparation for the next shuttle mission. Both crews participated in news conferences with American and European media. On flight day 11, the crews wrapped up joint operations, transferring supplies and equipment between Atlantis and the ISS. At 18:03 UTC, the hatches were closed, marking the completion of the primary mission objectives, including the Columbus module delivery. On flight day 12, Atlantis undocked from the ISS at 9:24 UTC, performed a fly-around for the station photography, and began its journey back to Earth. The crew spent the rest of the day preparing for re-entry. On flight day 13, the crew conducted final inspections and stored equipment in preparation for landing. They ensured all systems were ready for re-entry. On flight day 14, February 20th, Atlantis closed its payload bay doors, conducted a deorbit burn. It entered the atmosphere and landed safely at Kennedy Space Center 9:07 EST time, concluding the mission after 12 days 18 hours. The Columbus module is a key component of the International Space Station, designed as Europe's primary laboratory in space. Now, let's take a closer look at the parts of the Columbus module. Grapple fixture. The grapple fixture on the Columbus is a crucial feature that allows the station's robotic arm to grab and manipulate the module. This fixture provides a way for the module to be moved or serviced from the outside, ensuring the astronauts or ground control can reposition or perform maintenance without the need for direct human intervention during spacewalks. Inbuilt payload hosting facility, starboard side. On the starboard side of Columbus, there is an inbuilt Payload hosting facility. This external platform supports scientific instruments and experiments that need exposure to space conditions. It enhances the module's capabilities by allowing additional experiments to be mounted outside, extending the research capabilities beyond its internal space. Safety attachment points. Columbus is outfitted with multiple safety attachment points scattered around the exterior. These points are used by astronauts during spacewalks (EVA) to secure themselves while working outside the module. They ensure that astronauts can safely anchor themselves using the tethers, reducing the risk of floating away while performing maintenance or scientific tasks. Bartholomew platform. The Bartholomew platform is an external addition to Columbus, named after Christopher Columbus's younger brother. It provides extra payload capacity for hosting instruments and research equipment outside. Bartholomew allows for easier access to space exposure experiments and enhances the module's role in supporting a wide variety of scientific research. Internal racks for research. Inside Columbus, there are several internal racks designed to house research equipment and experiments. These racks are modular and allow scientists to install a variety of instruments for different types of scientific studies, including biological, physical, and material science research. The racks provide power, data connection, and environmental control for experiments to function properly in the space environment. The Columbus module has dimensions of approximately 7 meters in length, 4.5 meters, 15 feet in diameter, and a pressurized volume of 75 cubic meters or 2648 cubic feet. It has a mass of approximately 10,300 kilograms or 22,708 pounds. The module cost approximately $2 billion American dollars. In conclusion, the Columbus module stands as a testament to international collaboration and innovation in space exploration. As we continue to utilize Columbus for groundbreaking research, we can look forward to the valuable insights it will provide, furthering our understanding of the universe and understanding our capabilities in space. I hope this video on the Columbus module was interesting and informative. We'll meet you in the next video with another interesting module. Take care, bye.